So just to give an introduction, this is the first webinar of a series of webinars we are going to host over the next few months, through which we will showcase the latest addition to ToffeeX and discuss how these features can help you designing more efficient components. Today, this webinar is actually the first one, so we are starting with this one, and we would like to show you one of the latest additions, that is the so-called velocity target feature, and also show you how you can optimize. Sometimes just optimizing a part of a whole system can lead to increased benefits for the system itself. My name is Antonio Di Caterino. I'm one of the engineers working at ToffeeX, and I'm mainly responsible for customer success. This means a lot of serious different activities, but primarily my job is to be sure that your experience with the software and with the company is worth it. Together with me, there is my colleague Alessandro. Hi, Alessandro.
Hi, everyone. I'm Alessandro Canova, and I'm a core developer engineer here at Toffee. My background is in computational fluid dynamics, and my role is to develop new key feature that enables other companies to redesign their products and achieve better performance in a fraction of time compared to standard design tools.
Just to set the pace of this webinar, we're going to go through a quick introduction about who we are, what we do. We will then present briefly the case study we tackled and how we did it. And of course, we're going to show you and talk a bit more about the velocity target feature. To do so, we will first tell you about it, but also show you how to set up a design optimization problem in ToffeeX through a live demo. And at the end, after discussing the results, we're going to also have some time for a Q&A session. So let's start. For those of you who don't know ToffeeX, ToffeeX is a company developing a physics-driven generative design software. We are based in London, and we belong to the broader market of computer-aided engineering software. Our goal is to help companies worldwide to solve what we believe are some of the main pain points of the engineering design process. So we help companies accelerating their time to market, increasing their product innovation, and ultimately we empower them to create more efficient and more sustainable products. What we mean by physics-driven generative design, as the word suggests, is that the software uses physics to drive a design process. So it's empowering engineers to create optimized components in a fraction of the time and to meet all their requirements and all their goals. As you can see at the bottom, we have some of the companies who have already adopted ToffeeX, and they are spread across several industries, from aerospace to automotive to energy. And primarily, they're using the software to design and optimize complex thermal management systems. Now, without further ado, let's introduce today's issue. I would like to start by thanking the University of Parma that gave us the permissions to share these results and to use their activity, which was part of the EU-funded project Symbios, as a baseline for our design optimization. Just to explain it, the case we propose today is the re-optimization, the redesign and optimization of the flow delivery through the header of a heat exchanger that is coupled with a syngas generation system. This is actually part of a commercial grade system for the gasification of wood chips and pellets that is then used waste products as a feedstock, and that is located inside the campus of the University of Parma. The way it works is pretty simple, but also effective. There is a syngas going inside the core of the heat exchanger at a hot temperature, and this thermal energy is then transferred to the water that is flowing into the core of the heat exchanger, thus recovering the heat that is then used to provide heating to the campus itself. By analyzing the results of this activity, which are published in a paper that you can see here at the bottom of this slide, we realize that there is a good room to improve the whole process just by re-optimizing the header of this component. In fact, as you can see, the header in this case is simply an empty dome, which has zero control on how the fluid, the syngas, is delivered to the core of the heat exchanger. As you can see on the right-hand side here, we have a huge disuniformity in how the fluid is being delivered. But why is this a problem, Ale?
So typically headers are meant to provide a plenum volume that is used to even distribute the flow at the bundle intake. However, like in this case, sometimes happen that this volume is not sufficient to achieve flow uniformity. This can happen for different reasons. We can have like particular flow conditions, like a high flow rate, or we can have some constraints, some requirements that constrain the optimizer to work in what we usually call off-design conditions. And as a result, we can notice here that the heat exchanger is working mainly, we have two separate regions. The inner part that is receiving a surplus of flow rate, and the outer part that is almost not working at all. So to give more context, this translates into an heat exchanger, an equivalent heat exchanger with a reduced surface area, which leads to a reduction in the performances. However, as it stands now, the heat exchanger not only performs worse, but requires more maintenance for its life cycle not to be affected. So let me briefly explain, because this is strictly connected with this application. So the syngas flowing into the pipe bundle is rich in hydrocarbon and other volatile substances, which are prone to condensate if the temperature becomes too low. Clearly, as we can see from the picture on the left and the right, the purpose of the heat exchanger is to cool down these gases, but still keeping them at a temperature above the dew point. However, and we can notice from the pipe's position on the outer part, if the flow rate becomes, for some reason, too low, then the temperature drops, going below the dew point. The syngas condensation leads to the formation of what we call tar, which are oils, essentially, which are really sticky and tends to clog the pipe, worsening even more the situation.
So fundamentally, this, as you are mentioning, is a process that is worsening over time, and yes, it would be ideal if the flow delivery was uniform.
Indeed.
A typical design process in this case would involve several design iterations where the engineers are designing a component, trying to achieve a uniform velocity distribution at the core of the heat exchanger. So running validations, design validations again. Of course, this can take a long time. Also, it's not really easy to work with fluids, as you might know. So that's why we developed a feature that is called velocity target feature. As the name explains, this lets users to define a target in a design, in a region of their design of the optimization, inside which they would like to specify the software should design for a specific velocity profile. Alessandro was one of the engineers working on the development of this feature. So can you explain a bit more how does it work?
Yes, we have here the objective function definition, which is composed mainly of three parts. We have the difference between the velocity and the velocity target that we want to specify, and the region of interest where we want to measure it. In this example, we can see here on the right, this green box, which is the region that we want to measure this difference. We have also this matrix defined in the middle, which measure the relative importance of this objective function compared to others, which can be, for example, pressure losses. And therefore, we can decide which is where we want to go from a design point of view. But it's also more important to select and define which component of the velocity target we want to optimize. In this case, for example, we are interested only in the vertical component.
Well, trust me when I say it's easier done than said in this case. So that's why we will show now a live demo. So let me go to the next slide and simply sign in into our platform. As we are in ToffeeX now, this is the main page, the home page of the software, which we also call as the project page. As you can see here, we have already some pre-existing old projects, and you can think of the project as a folder in which you are storing the design or the validations that you are performing for a specific objective. We have created already a project for today, which is obviously called Velocity Target Webinar. And once we click inside and we access the project, you can see that you have a page which is split between domains and toolboxes. A domain is simply defining the three-dimensional space that can be used by the software to create a component. And it's also describing the physical space inside which the simulation can be modeled. For reasons of time, we have already provided the domain. So You can see it's already here. But let's create together a toolbox. A toolbox is instead what we define as the main operational environment within ToffeeX. As the name suggests, is giving you all the tools to operate on the domain. So let's start with the creation. We will give it a name. So in this case, it's going to be webinar. You can give it a description if you need to take some notes about what you're trying to achieve with this specific toolbox. Of course, it will need a domain to work. As we said before, a toolbox is what you use to operate on a domain. In the dimensionality, we are defining how complex the software can create a design. In this case, we are telling the software that it can go and create a geometry with a complexity that is three-dimensional. In this case, we are going to disable the thermal effect because we are only interested in optimizing for the fluid characteristic. So we want to have a design which is distributing the fluid in the uniform way, as we mentioned before, and also minimize pressure drops because we don't want to block the process. So let's click on create. Once we click on create, the software will redirect us inside the toolbox itself. And the first time you do that, it's going to also ask you to create a run. A run can be of three different types. So you can have a mesh run, a simulation run, or design run. Obviously, with a mesh, you will be creating just a computational mesh. Physics simulation lets you run a CFD simulation, while design lets you create the actual component, the optimized component, based on a series of settings that we're going to specify now. As you can see here, we have our domain, so which was uploaded before. So you can see here we have specified the inlet of our domain. Here we have all the outlets, so a lot of them with several numbers. Let's click on create, and you can see that now on the sidebar here on the left, we will have the run details, and we're going to have settings to define all the parameters we want to use for design, simulation, and mesh. Let's start by expanding the design settings. In the design settings, first of all, what we want to specify is the volume we mentioned before, inside which we are applying the velocity target, optimization target. There are several ways to create the volume. In this case, we will simply click on add and use the controls of the GUI. So as you can see here, you can place this volume, you can move it around, and you can also scale it into three different directions. So just for the sake of time, let's show quickly how we can do that. This should be crossing the region we want to target. So we have identified the region which is representative of the outlets of the headers, inside which we would like to specify the velocity target. So just for reference, let's call this volume BT, standing for velocity target, and click create. The next thing we have to do is to specify the objectives of this optimization process. So as you can see here, we have an icon telling us that this is an input needed, so the software can't run a design optimization without objectives. In this case, as we mentioned before, we disable the thermal effects, so we only have the opportunity and the possibility to optimize for pressure losses and for this velocity target. Let's start by enabling the pressure losses objective. This is going to be the reference of the optimization. So if you consider the multi-objective optimization, this will be the weighted sum of different optimization functions. So in this case, we will use a weight of 1 for pressure losses, just for it to be our reference during the optimization. The next one we will specify is the velocity target. So here we can give a name to the target. And again, I will use Alessandro's help to set up this optimization target. What should I use here?
So first of all, we need to select in the volume region, the region of interest where we want to measure this difference. Then we need to specify the components of the velocity, which are our target. In the XY component, we're gonna simply put 0 and 0, not because we want to force them to 0, but simply because soon with the weight, we're gonna tell the optimizer to simply discard from the evaluation these two components. For the Z direction, which simply takes the flow rate and divide by the number of outlets with the area, and in this case, we get 6.6. It's important to set also the direction. So in this case, it's minus Z, so minus 6.6.
Okay.
For the weight, as we mentioned before, we set 0 and 0 for the X and Y, which simply tells not to consider them, and a weight of 10 to tell the optimizer that we are interested in a geometry that match close the velocity target.
Okay, once everything is completed here, we can click create and the software will get this one as one of the optimization objectives. For the design material, we'll be using steel just as the material of the header. So click on update. And of course, we don't want just to make a part which is looking good, but we also want something that is manufacturable. Here we have defined the objectives, but as part of the constraints we can apply in the software are also the manufacturing constraint. In this case, we will select some constraints for additive manufacturing. So we want to take the benefit of using this 3D complexity the software is offering us. But we know that also for additive, not everything is simply a plug and play option. Just press a button and everything will work. In this case, we are interested in manufacturing the part with an SLM process that requires the geometries, at least the internal geometries, to not be overhanging more than 45 degrees. So in this case, what we can specify is simply this 45 degrees angle, specify our build direction, that in this case will be aligned again with the Z axis. So just specify 0, 0, and 1. And here select what are the supported region. So in this case, the base of the header, which is here, will be our base support region. And click on update. We have defined our targets, so now we need to define what is the physics supporting this optimization process. So let's expand the simulation menu. Here again, you will find some required conditions, in this case, the fluid properties. We have some predefined values also in this case for air, water, or for ethylene glycol. But in this case, we are working with the syngas, which has a slightly different fluid, say, thermophysical properties, which in this case are...
for the density, we can consider values around 0.4, 0.5. And the kinematic viscosity is slightly higher than air, and we have 1 e to the minus 4.
Misclick. Thank you, Ale. Okay. Last bit, we need to define the boundary conditions. So as we showed before, we have an inlet here highlighted, but we need to tell the software what are the conditions here at the inlet. So let's start by creating a boundary with a type inlet. We're specifying here a fixed velocity, and Alessandro was said before, we have a value of 30 meters per second as our input condition. And here, among the surfaces, we can select the inlet surface and simply create. We will repeat this process. So we go to the outlet. Here we have created a group of surfaces grouping together all the outlets just for a quicker selection. And we're going to simply use a zero gradient condition with a zero pressure outlet. Simply click on create. And finally, we have to upload all the walls. So we have some walls here, which are the side walls of this component, and also the default wall that have been created. Sorry, the default wall that has been created. Okay, the icon has disappeared, meaning that we have provided a boundary condition to all of the available surfaces in this domain. Finally, we move to the mesh, which is used to create the computational grid. In this case, we will just show you how to create basic cells, basic mesh. So using either a number of cells. In this case, we actually use a cell size. So we specify a value of 0.2 meters to be sure that we are able to capture the feature of our design. You also have some other options in terms of local refinement. So you can refine within a volume you can specify on a surface, or you can add some inflation layers to capture the behavior at the boundaries with more accuracy. Once everything is defined, you can click on this icon and you can select the computational power you want to allocate for this optimization to start and to run. In this case, let's select 18 cores and click on launch. This takes some time. We're talking about hours, so of course we don't have the time to wait now. That's why we have pre-run this geometry before. So here we can see this is the structure which has been designed. So just showing you again, this was the original domain we provided. This is the solid result that is built. So you can see how it's building this component to deliver the fluid at bottom of our design. And also, let's just make this more transparent. We can also see the fluid which is going inside. So you can see how the fluid is split into the different regions just to accommodate for the velocity target distribution we specified. We have downloaded the results, but now I would say that it's better if we go back to the slides so we can comment them with more detail. Ale, can you tell us a bit more?
Yes, we can see here from left to right the solid, the fluid, and more importantly, the velocity distribution at the outlet. Regarding the solid, it is important to underline how the final geometry that the optimizer has built and created is self-supported. This, as we mentioned before, is obtained by constraining the optimizer to only search and build for structure that satisfy the overhang constraint. Moving on now to the fluid and to the distribution that we can see here, we can immediately see that it's more uniform compared to what we had at the beginning, so the empty dome. And indeed, this improvement is captured by the velocity objecting function, which goes from a value of 202 to a value of only 15. In this way, each pipe receives almost the same amount of flow rate, maximizing the heat transfer. Additionally, there is a small increase in pressure losses, and we have an increase of 50 Pascal, so something really small. In order, and you can see here, to assess the improvement in the heat transfer, we perform an additional validation by considering this geometry and the whole heat exchanger. And this validation show a 12% increase in heat transfer.
Okay. As we mentioned before, we also included the overhang constraint to be sure that the geometry is self-supporting. So here on the left-hand side, we have the geometry we are showing you now, we showed you before, which was optimized using this control of the overhang. So all the structure are self-supporting, considering the 45 degrees angle with respect to the build direction, which is here highlighted with the green arrow. On the right-hand side is that we have a geometry which has been optimized for the same objectives, so same parameters, but the only thing is that there is no control on the overhang, and you can see how the top region here is actually it's going to need supports internally to print in this direction. What we are comparing here, of course, is also the performance. So how this constraint is worsening the performance of the part, because every time you impose a constraint, usually you can expect a worsening of the performance. In this case, it's very minimal. So you can see that the value of the objective function, which measures the distance between the velocity target and the velocity distribution in your domain, is very small. We are talking 15 against 13. Of course, the smaller, the better. Same for the pressure losses, but again, we are talking about small values. We have here some print samples. These are made with our fantastic SLA printers in the office, which is sometimes very messy, but we can see here on top left, the geometry, just a section, so it's just half of it, but it shows how it's been printed without any support. Here on the bottom, we have instead the representation of the internal solid, while on the right, we have with clear resin, how the part would actually look like. So we are showing now just the internal structure of the dome, but we know that we have to preserve the shell outside, the connection to be mounted on the rest of the heat exchanger, and so forth. These are all things you can control in ToffeeX, all things you can adjust. So all manufacturing and design constraints can be included just to be sure that the part you're designing is then compatible with your system. Just some final consideration. So today we showed you how to use a feature that we have recently developed, so this velocity target feature, to reduce the spread, that kind of non-uniformity we were having in the header of the heat exchanger. And we also showed how sometimes you can just optimize a part of the system to optimize the performance of the whole system. This is also leading to a reduction of the tar deposition or a more uniform tar deposition over time, which will probably lead to a shortening in the maintenance cycles. This is something we're going to assess. So we are planning to print the part, so with real dimensions, with real materials, and test the part in operation. So stay tuned for more updates on this one. We went a bit longer, but now I would say we have some minutes for the Q&A. Of course, if you can stay, no worries, just the session is recorded or just reach out to us. I want also to mention that this is the first webinar, again, of a series. So we're going to show in future how to optimize other designs or, for example, just the core of the heat exchanger and show how you can use different features to solve different problems. We have the Q&A box, so please use the Q&A box to ask questions. We're going to look on a different monitor now, so if you see looking right and left, that's why. Of course, thank you everyone for attending. Okay, so we have a question for everybody, just for the benefit of everyone, I'm going to read it. So how can I impose constraint based on half design condition? For instance, minimize the pressure drop and meet the velocity target on a design condition A, and maintain the maximum surface at temperature within a threshold at off design condition B. Okay, so you're talking about optimizing for a condition, but seeing how the part performs in off design condition. At the moment, this is not something we can do. So the optimization will be for a single predefined set of parameters, and also just for a single condition. What you can easily do actually in the software is to use the geometry you have designed and simply test it for different conditions. So maybe you can optimize for the design condition and test it for off design and see how that works. You can also perform multiple optimization for both design and off design conditions, and then you can simply understand what are the key elements that make the difference in making the part optimal for one condition or the other, and then you can just do some post-processing by yourself. ToffeeX is a tool, so it's not like just magic. So of course, any engineering choice that you can make or any engineering decision in terms of post-processing is still required and can also lead to better design. You should consider it as a tool to empower your design capabilities. I hope this replies your question, this answers your question. So we have another question that is, can you add a machine tool constraint to the optimized design? For example, a tool that passes to machine the geometry. So yes, we have both constraints for additive or for traditional manufacturing. One of these one is indeed machining that let you specify both the direction of the machining tool and the sides of the head of the tool. So for example, if your tool has a diameter of 4 millimeters or 1 millimeter, this will have a difference on the optimized geometry. So you can see how the cooling channels being designed are different given the different constraints. In short, the answer is yes, but please reach out to us so we can give you more explanation and more detailed explanation and some examples. Okay, I don't see more questions coming. This means probably we were so clear and everyone is satisfied with the presentation we had. Actually, one is coming now. Are there any consideration for fixturing in the machine tool solution? If I understood your question correctly, not at this moment, but this is something you can consider as an engineer. So you can constrain some of the design, some of the parts of your design to be preserved during the optimization. So let's say in this case, we have the header of the design, but we also have the flange around with the holes. You can either combine the design you optimized with this external dome with the flange, or just use the whole design domain and keep the flange as it is during the optimization process. So the software won't break the structure you are preserving. We have a question from the result of the simulation. It is clear that inlet flow is subdivided into manifolds. Have you tried to compare the results of the optimization with a more conventional one? Not sure about the question because we compared the design with the original one, which was simply a simple empty dome. In this case, yes, we compared with that and we showed how the software designed something which was more efficient. I'm not sure if I got the question.
But yeah, we haven't found any other description about this geometry rather than the simply empty dome. So we took this one, which was shown in the paper and the publication as our reference.
One more question is about, we have showed what is the time required from initial design to final design, and what are the computational requirements around the simulation? So thank you for this question. It's actually something we didn't explain before. The software is a cloud-native software, and when you subscribe to a license of the software, you will be given some computational power. So everything is running in the cloud on high-performing computers. We are also on Amazon Web Services. The time from initial conception to the final design really depends on a list of different parameters, which are the mesh density, mesh resolution, the complexity of the problem itself. But in general, the average time is between a couple of hours and say 10 hours. So we are talking about a very short time to start from a an empty design to something which is optimized for a scope.
The goal is also to launch simulation after evening or like after the working day and achieve a complete result by the next morning. So this will allow to a faster iteration of the design and to finalize everything in the fastest way possible.
Yeah. Other question is, have you validated any of your optimized designs? Yes, otherwise we won't be here as a company after 3 years. So most of the design, unfortunately, are covered by NDAs. So as I mentioned in the beginning, companies that we are working with are in the aerospace, automotive, so are quite secretive in terms of the applications they're working on. But yes, we have done validations. There are some things that we can't capture in terms of the physics. For example, if you're 3D printing, for us, it's almost impossible to understand what is the roughness of the component. So this might affect the heating transfer in the actual operational life. These are things that, of course, are I would say quite common in any CFD simulation. So again, I would mention that ToffeeX is a tool of engineering design. You will be using it kind of on a daily basis to create optimized components. But then the validation with more accurate results or the experimental test could differ from the simulation, as you would expect. But in general, with the topology optimization, you are finding the optimal trend of the design. And again, it's speeding up the going from a concept to a final design in just a fraction of time. One more question, again, on CFD mesh and turbulence model. So the CFD mesh we use is a structured hexahedral mesh, so something that we know works best with CFD problems. You can apply refinement layers, as I was mentioning before. Turbulence, for this one, we use a K-epsilon model, but we also have the options for K-omega or K-omega SST, so depending on the applications, you can include and work with different models.
Yeah, in this case, we simply select K-epsilon because what was the one used in the publication, so we try to keep everything the same and improve from that the geometry by keeping the same physics.
Okay, I would say maybe just take one more question and then we can close this meeting. What was the file size for this model after exporting? If I remember correctly, we are talking about 50 to 100 megabytes, so quite small in this case. The results you get from the software can be in different formats. So you can export an STL describing the geometry, or you can also export step files in some cases, or just field files. So you can have a look at fields to understand all the different quantities like the temperature, velocity, and so forth. So, well, thank you everyone for this Q&A. I hope this session was really interesting for you. Also, thank you for the questions. It's always good to reply to your questions, and also it makes you realize what we were not clear in communicating. Again, thank you very much, and I hope to see you also for the next webinars, and I wish you a good day.
Thank you.